In this problem, we are given a beam that is fixed to a wall at K and is propped up by an elastic rod on the right hand side. Using the principle of superposition, we are asked to determine the load carried by the member TH. By observation, we could say that this problem is indeterminate because static analysis would give us three unknowns: Mk, Ky, and Fth, but only two equations of equilibrium. We would therefore need additional compatibility conditions to solve for the unknowns.
To solve this problem using superposition, we would need to identify different load cases. Since there is an elastic member at T, we would need to find out the total deflection at this end. Two of the load cases in this case are more obvious. For load case 1, we have a uniformly distributed downward load Q between K and B. In this case, total length L equals to 3L prime, a P naught equals to a downward minus Q, A equals to an L prime, and P equals to a 2L prime. From the appendix we get, in this case, let the deflection be equal to Vd1. From the appendix we get Vd1 equal to a minus QL prime cube divided by 24 EI multiplied by 4 times 3L prime minus L prime, which equates to minus 11 over 24 QL prime to the power 4th divided by EI. The second load case, we have a applied clockwise moment MC at C. In this case, the total length L is 3L prime again. MC being clockwise, we have M naught equals to a minus MC, A being equal to a 2L prime, and P being equal to an L prime. If the deflection of ND in this case is Vd2, we have Vd2 being equal to a minus MC times 2L prime divided by 2EI multiplied by twice of 3L prime minus 2L prime, and this simplifies to minus 4 MC L prime whole square divided by EI. Before moving on to the next part of the solution, let's go ahead and call these equations equation 1 and equation 2. For the final load case, we have an axial load coming in from the elastic rod. Let's assume that this force is tensile and its magnitude is equal to FTH. Notice that end H is fixed with respect to the ground. For this case of loading, we are going to have the total length L equals to a 3L prime and P being equals to a minus FTH, the negative sign because FTH is pointing downward on the beam. From the appendix, we have Vd3 equal to a minus FTH times 3L prime whole cube divided by 3EI, and this simplifies to a minus 9 FTH times L prime cube divided by EI. By superposition now, we know that the deflection at end D is going to be the sum of all three deflections that come from equations 1, 2 and 3. In other words, we can say Vd is equal to Vd1 plus Vd2 plus Vd3. Also, from our knowledge of axial deformations, we know that due to the tensile force FTH, the upward displacement of node D in the rod TH is going to be given by Vd rod equals to FTH times L prime, which is the length of the rod, divided by EA. Let's go ahead and call these equations 4 and 5. We know that equations 4 and 5 are going to be same. So substituting one, 2 and 3 into equation 4 and comparing it with 5, we will have FTH times L prime divided by EA, and this comes from equation 5, being equal to a minus 11 over 24 QL prime to the power 4th divided by EI, which comes from equation 1, minus 4mc times L prime square divided by EI, coming in from equation 2, and a minus 9 FTH L prime cube divided by EI, which comes in from equation 3. So if we solve this equation for FTH, we will have FTH equal to a minus AL prime square multiplied by 11 QL prime square plus 96 MC divided by 24 times I plus 9 A L prime square. This is the force that we wanted. Note that this is compressive both with respect to Q and MC, which would agree with our intuition. This brings to an end the solution for homework problem 7.4.